I'm Andrew Bogart, and my partner is Jennifer Mullican, and we're going to do a presentation over grading monochrometers.
First, just an overview of what it is. A grading monochrometer is the part of a spectrophotometer that separates different wavelengths from one another and selects a narrow band of wavelengths to pass through the sample. Here are some examples of gratings that are used to diffract the light in a monochrometer, and we're going to talk a little bit more about how they work in a little bit.
I'm going to talk to you about how it works. Right here we have a white light source coming through the entrance slit, and then at the concave mirror, the light is then collimated and made into parallel rays, and then it's reflected off the mirror onto the grating, and then after it hits the grating, which the grating works a little bit different than a mirror, after it hits the grating, it's going to hit another concave mirror, and after that mirror, it's going to come out the exit slit right here. As you can see, we have white light coming in right here, and then at the exit slit, we just have one color. And the best way to select the different wavelengths of light is you can rotate this grating right here. So if we rotated it up a little bit, we make it green light out of the exit slit. I'm going to talk to you about the grating. As you can see, it's many sawtooth edges right here, and then when the light comes in, it's going to be reflected off of these little sawtooth edges. And just to tell you how small these little grooves are, there's 600 to 2400 grooves per millimeter, and each one of these grooves is parallel and equally spaced. Jennifer's going to talk to you a little bit about diffraction.
All right, here's just another example of grading. When light is reflected, each groove behaves as a source of radiation, diffracting in all directions, which creates constructive and destructive waves. Each color has different wavelengths, so the rays don't all have constructive waves, and therefore the waves separate in space. In order to get a different wavelength, like Andrew said earlier, the grating is merely rotated. All right. If the adjacent light rays are in phase, they reinforce one another, which leads to constructive interference, as shown there. If they're out of phase, they cancel each other out, which is destructive interference.
And I'm going to talk to you about the grating equation. For each incident angle theta, there are diffraction angles phi, at which a given wavelength will produce maximum constructive interference. Therefore, filters that reject many wavelengths are used to select a desired wavelength and reject other wavelengths. Some types are absorptive and interference filters. And this right here is an example of the white light spectrum that would enter through the entrance slit and what it would look like when it exits through the exit slit as monochromic light. So right here we can see that we had all the light coming through, and then when it comes out, we just have this one right here. That's pretty much how monochromic grating works.
Some applications of grading monochrometers. They're used in automatic scanning spectrophotometers. This includes a mechanism to change the wavelength selected by the monochrometer and to record the resulting changes in the measured quantity as a function of wavelength. Another use is the absorption spectrophotometer, which measures the absorption of light by a sample as a function of wavelength. Monochrometers are used in optical instruments that measure other phenomena besides simple absorption or reflection, wherever the color of the light is a significant variable. For example, circular dichroism. Lasers can also be used. Monochromatic light allows for the measurement of quantum efficiency of an imaging device. And here is just an example of a spectrophotometer.
Thank you.